Okay, hello.
Hello.
Here we go. Acids and bases.
Bases and acids.
This is a big part of the AP test. It's like 17%, which
That's
is
a lot.
twice as much as all the other topics. So this is a big one. We need to
Right.
take care of this one.
But lemon juice is one of my favorite things.
And you know what? It's an acid.
It is.
You know, and coffee tastes bitter, but it's not a base, even though people say bases taste bitter.
I don't think it tastes bitter myself.
I
Kind
love
of one of
coffee.
also my favorite things.
Okay, so today's lesson is just about kind of what acids and bases are. So we're going to be going through a couple different models of acids and bases. So we're going to start with the basics.
That was bad.
Basically, okay, so some properties of acids. Well, you know what they are, right?
Yeah.
They taste bad,
Yeah.
sour.
Slippery.
No, bases are sour.
Oh, that's right.
Acids are sour. Bases feel slippery,
Right.
kind of like
Sorry.
soap.
I was reading the screen. So, Sour Patch Kids.
Exactly. Citric acid.
Yes.
Right?
Yes.
All right, don't be tasting things, any of you, to find out if they're acids or not, okay?
Yeah, we don't do that.
Okay, so Arrhenius. Our first model of the acids and bases is by this guy named Arrhenius. Not the same thing as the Arrhenius equation, which we learned before. I don't know if it's the same scientist or not.
I think it
seems
is.
pretty likely that it is.
Yeah.
The two completely different subjects. And sometimes I have to tell you, Ms. Woodard, we call it the Arrhenius equation.
Well-
not for acids and bases, but for...
I'm not going to tell you how I remember
Okay.
the name because it's not appropriate.
Okay, moving on. Okay. All right, so Arrhenius acids, acids when they dissolve in water produce H plus ions, and bases produce OH minus ions. Okay, so that's a very simple model of acids and bases, and that's where we started, and that's kind of how we learned how to name them in the fall, because everything that started with an H, we called it an acid, because that was the H plus ion, and everything that had OH in it, we called it a base, because of the hydroxide ion. However, we need to expand our minds a little. We need to go bigger. Okay. All right, so here's a couple of look-sees at the Arrhenius model. So notice we have the yields reversibly sign there. So equilibrium is going to play a big part in this whole situation coming up.
Didn't you guys just learn this?
Yes?
All
So they
right.
know what that means. And typically, acids and bases, when they set up an equilibrium, it's either going to be a weak acid or base that's going to be far to the left, or a strong acid or base, which basically goes to completion. I'm going to try to stop saying basically. Don't say basically. All right, so.
Essentially.
Okay. Acid, base. So acid produces H plus, base produces OH minus. And that's what gives us the pH scale, which we're going to get to soon. Now, Bronsted-Lowry came along and decided that this definition was too limited. Because there are some other things that act like acids and bases that don't have H plus or OH minus. Okay, so now we're going to think about more in terms of an H, we're going to call H plus a proton, okay? We just learned about this in CP Chem. So hydrogen has one proton and one electron. You take away the electron, all that's left is a proton. So H plus is sometimes referred to as a proton. So an acid, instead of producing H plus into the solution, is donating a proton to something else, okay? This is how I like to do it. So I have my pen, I'm the acid, because my pencil is my proton. You're a base.
I'm a base, basically.
Here you go.
Oh, thank you.
Now,
I'm an acceptor.
exactly. So the acid is a proton donor, and the base is a proton acceptor. But now, look what happened. Now she's an acid, because she has the proton.
Ooh,
And now I'm a base, because I don't have the proton anymore.
sour.
Slippery!
Okay, Now, since I'm the acid, just so we can do this again.
Yeah.
I'm going to donate this to you.
Okay, now I'm the acid again. I've
And
gone back. Okay, because it's an equilibrium system anyway.
Exactly. So now I'm slippery.
Yes, and now I have the
so.
proton. Okay, so now I have the proton that I can give to somebody else. You want it back?
Sure.
Okay. Now I'm the base. Okay, so what happens is we have the proton donor and the proton acceptor. So the acid is the proton donor, gives off the H+, so that's very similar to Arrhenius. The base is the proton acceptor. So instead of having anything to do with OH, okay? So, we're going to forget that. Now, we call these guys conjugate acid-base pairs. Okay, so again, let's do the starting again. So now I'm the acid because I've got the pencil. This
And
is
I'm
my
the
H+.
base because I don't have one.
Right? Now, I'm going to donate my proton to her. Now, she's a acid. Now, what happens with the species that are left over is we call it the conjugate acid. So now, I was the original acid, she's the conjugate acid.
Mm-hmm.
She was the original base, now I'm the conjugate base. Okay, so the ones that are on the reactant side are usually called the acid or the base. The ones that are on the product side are the conjugate acid and the conjugate base. Okay, does that make sense?
Totally.
Okay.
I'm with you.
So they're pairs. So they work together in pairs. So when you're looking at a chemical reaction, you're looking for the same species that has an H on the left, but then has a missing H on the right. And then, or one that gains an H on the right. Okay. Now, oh my gosh, here's the classic. It's really funny. Acids and bases are so funny. It's just like, ha, ha, ha.
We crack ourselves up over here. It's fine. It's fine.
HA, I'm going to write on the board a lot, and anytime we do, we can say ha, ha, ha.
Ha ha ha.
That's our generic acid.
Okay.
And it's funny. It's a funny acid. But if it reacts with water, notice what happens. The HA gives its proton to the water and becomes H3O+. Mm-hmm. And then A- becomes our conjugate base. Okay, so HA is the acid, A- is the conjugate base. So in this case, water is acting as a base, and H3O+ is the conjugate acid.
And it's weird, right? Because we normally don't consider water to be a base. Mm-hmm. But in this case, because it's accepting, it can be.
Exactly. Isn't that cool?
It's really cool.
So water is amphoteric. It can do both. It goes both ways. It can be an acid or it can be a base. So cool. Okay. Oh, there it is. Acid, base, conjugate base.
You should give them a second. Oh, here we go.
And here's the diagram.
I wanted to give you time.
All right. So conjugate base is everything that remains after the acid molecule or the proton is lost. And then the conjugate acid. So again, if you think about it as the reactant side versus the product side, the acid and the base are on the reactant side, and then the conjugate acid and conjugate base are on the product side.
Here, do you want to move us up to the corner so they can see what they're missing over there?
Sure.
Okay, there we go.
Okay.
Cool.
Should we get rid of this? Can we hide this? Does it go away?
They can't see it. You're just hiding that from us.
Oh, I think they, okay.
Okay.
All right, now, what happened?
Nothing.
But it turned, okay, there we
We're
go. Okay. Let's just open these up and then we'll talk about them. Okay. So strong acids and strong bases. Oh, thank you.
Yeah, you're welcome.
Okay, so all the rules for equilibrium apply when you have that yields reversibly symbol. So if it's a weak acid, it's going to be far to the left on the equilibrium, so it's going to be reactant favored. If it's a strong acid, it's going to be far to the right, so there'll be more H plus in the solution, so it'll have a very large equilibrium constant.
So strong acids are really good at giving away their protons.
Exactly. They're like, you get a proton and you get a proton.
They're like
and you get a
Oprah.
proton. Yes.
They're the Oprah of
Exactly.
acids. Okay.
So if they're the Oprah, then what would be the weak acid? Who doesn't want to give away their protons?
Me.
I like my protons.
I do.
I'm going to keep them.
They're cute and stuff.
Okay.
Okay.
All right, let's keep moving. Why does it keep going like that?
I think it's just because.
Oh, I clicked on it.
Yeah.
All right, so here's our equilibrium expression. All the same equilibrium rules apply. Okay, so products over reactants raised to the power of the coefficient. And notice that we have capital K is our equilibrium constant, and we have a little subscript A. So this one means Ka means the acid dissociation constant. So it's an equilibrium constant for an acid. And notice what's in the numerator there. It's H3O plus. Okay, so that's going to be important when we're calculating pH later on. Okay, now chemists like to use the same word, different words for the same things, or different things for the same, to meaning the same stuff.
Right.
So a lot of times you'll see H3O plus and H plus, either one of them represents a proton. And we call that H3O plus, we call it the hydronium ion. And so
I like that name.
I know.
Hydronium.
Hydronium ion. And
I
it
know,
really
sound
does.
fancy.
It does. And it makes you sound like you really know what you're doing.
Well, from what I hear, your students really do know what they're
They're
doing.
good.
So
They're so smart.
It just fits.
Yeah. Well,
Yeah.
and we need the right words. 'Cause
Exactly.
that's where we are. Hydronium ion, it also gives you the sense of two water molecules when they interact with each other. One of them becomes a hydronium ion, one of them becomes a hydroxide ion.
Right.
So anyway, H3O plus and H plus essentially mean the same thing. Okay, so if you notice in the equilibrium expression up above, we have it written either way, and those basically mean the same thing. Okay, so you can write it either way. I never do the animation links. Oh, that's the end of the section. Okay, we're going to stop there.
Sweet. This was getting long anyway.
Yeah,
Because,
we're done.
yeah.
How do I get out of here? Aha.
You have to, yeah.
Stop sharing? No. That's
Well,
not
yeah,
what I
we can
want.
stop sharing.
I want to go up here to this.
Yes. And that's how we stop it.